Alright, now we enter the new chapter called wave properties of particle. Okay, what is a wave? Wave is continuous energy, whereas particle is just a particle, yeah, with mass. Okay, so here there's one example that a particle can be also wave. Okay, and for this chapter we will concentrate on electron. Okay, that means electron, although it is a particle, sometimes it can behave as wave also. Okay, before we talk about electron, okay, let us first consider what is means by wave particle duality. Wave particle duality. So wave is this, the continuous energy, transfer of energy. Particle is actually something you can see, yeah, something discrete. Okay, duality means it has two property. It has two property. It has wave property and also particle property. Okay, so what is actually definition of wave particle duality? Wave particle duality is the phenomenon where under certain circumstances a particle exhibits wave properties, but under other conditions a wave exhibits properties of a particle. We cannot observe both aspects of its behavior simultaneously. Okay, so what you can see here is they say under certain circumstances. Under certain circumstances, it is a wave. And under other, okay, maybe I can put this using other. Under other conditions, it exhibits particle property. That means under certain condition, it is a wave. Under other conditions, it is a particle. We cannot simultaneously exhibit both properties. You cannot have certain conditions. You can see two properties at once. Yeah, you cannot see two properties happening together. Yeah, there's no such thing. Let us. That means it only certain condition. For every condition, it only exhibit one kind of property. Only exhibit one kind of property. It's either wave or either particle. But it won't exhibit two properties simultaneously at one time, at one conditions. Yeah. But the special things about this wave particle duality is it has both properties for different conditions. Okay, so what you can see is in previous chapter quantization of light, you learn about electromagnetic radiation or visible light. This light has wave particle duality. That means under certain conditions it is a wave, under certain condition it is a particle. Yeah, but you won't have a wave and particle together. So look at this light. So I have two examples. In previous chapter, we have already learned about light. Okay, light. First talk about light. Light sometimes behave as wave, sometimes behave as particle, but it won't behave wave and particle together. Okay, so why I say certain condition it is a wave? For example, in previous chapter also in physical optic we learned that light can undergo interference, isn't it? This is what we call the interference in the Young double slit experiment. Young double slit. So it is you see what you can see is it form fringes. Yeah, it form what you can see on the screen. You can see there is fringes. If you imagine, if you think that light is a particle, like you see here, there are two slits here. If light is a particle, okay? If light is a particle, so the light passes through these two slits, two particle. Here you have two particle going for two slits. So on the screen here, supposed to have only two fringe. Yeah, what I mean is you should see something like this on the screen here. You should see something like only have two fringe. But that doesn't happen. What you see is a range of bright fringes. You can see bright fringe, dark fringe, bright fringe, dark fringe, instead of just two. If light is a particle, like what is shown here, you see, if light is like a particle, like two particles here passing two slits, you should see the particle only gather at two fringes. Yeah. If the light, let's say if the light shoots out a lot of particle, the light shoots out a lot of particle, but all the particle just all the light will only pass through the two slits here. You understand? Only pass through the two slits. So in the end, on the other side on the screen, you should see only two fringes of particle. But that doesn't happen. What really happened is you see more than two fringes. You see a lot of fringes, a lot of bright fringes. So light in this condition do not behave as particle. Yeah, light in this condition do not behave as particle. It behaves as wave. Why we say wave? Because if we think that light is a wave, then we can explain this phenomenon. Why it produces this bright fringe, dark fringe? Okay, because of the, you learn about the path difference. You still remember you learn about the delta L? Delta L, you learn about delta L, you learn about delta L if equal to m lambda, then it produces bright fringe. If it is an in-phase source, okay, if it is an in-phase source, if the path difference, talking about wavelength, wave, we are talking about wave. We consider light as a wave. If the delta is m lambda, produce bright fringe. If delta L is equal to m plus half lambda, it produces dark fringe, isn't it? So for Young double slit experiment, the light can be only explained as a wave. It only exhibits wave properties. It don't exhibit particle property. That's why I say it only show one property at one condition, at certain condition. Only one property, that is only wave. We cannot say light as a particle, because if light is a particle, you won't produce so many fringes. It should only produce two fringe. Okay, for this condition, light can only be explained by wave. Light as a wave, and because of wave, we can talk about path difference. Yeah, because of wave, because we think that light is a wave, that's why we can say we can talk about path difference. Path difference is only for wave. Understand that? For interference. And then also we have diffraction grating experiment, which I didn't show here. Diffraction grating, also something like interference. Okay, also talking about path difference. We also have path difference there. So for this condition, light only behave as wave. Okay, light only behave as wave, like this one you see. For purple light has a very low wavelength. For red light has a very long wavelength. This is one example. Even different color has different wavelength. Do you remember or not? Even the Young double slit or diffraction grating, if you use red light, we will talk about the separation between fringes. We talk about the separation between fringes, which is delta delta y equal to lambda d over d, isn't it? Delta y is what? The separation between fringes. It depends on the wavelength. So light is a wave in this condition. Light is a wave. And red light, this is the red light, this is the violet light. We know that red light, like this one, the red light is a very long wavelength, 700 nanometer. If the violet, do I have a violet here? The violet light, the wavelength is 400 nanometer. Okay, so if let's say if long wavelength, like this, the red light has a very long wavelength. The red light has a very long wavelength. So if long wavelength, you will see the separation between fringes very further from each other. Further from each other. So for the delta y for the red is very further from each other. So what you see on the screen here, on the screen here, you can see the fringes very far apart. Very far apart. Very far apart. You understand that? I mean the delta y. The delta y. Okay, very far apart. If you're using a violet light, violet light. Okay, we know that the violet light. Let me just throw this off. Okay, if I use a violet light has a very short wavelength. Okay, so the delta y should be small. Yeah, so that means if the wavelength is very small, you should get a small separation between fringes. So if you use violet light, you should see something like this on the screen. I should use a violet. You should see something like this. Very close to each other. You understand or not? You should see the separation very close to each other. Yeah, the delta y is so small on the screen, and you can see more fringes on the screen. Yeah, provided the same size of the screen, you should see something like this. Understand? So light behave as wave. And because light is a wave, we can talk about this separation between fringes. Because it depends on the wavelength, we think that light is a wave. Yeah, you see, light is a wave. The red light has a very long wavelength. The violet light has a very short wavelength. So light only shows wave properties here. It don't show particle property. Yeah. So in certain conditions, you only exhibit wave property. But in other conditions, it exhibits particle property. So in what conditions the light shows particle property? Just now we talked about light is a wave. How about particle? Light behave as particle in photoelectric effect, and also Compton effect. Compton effect you don't study in your syllabus now. Okay, this one maybe for other time I will talk about it. But in your syllabus now, you're not learning about Compton effect. It's about X-ray diffraction. Something about maybe you can Google it. What is about Compton effect? Compton effect also describe light as particle property. It also exhibit particle property in Compton effect. Yeah, for the light. It's about X-ray diffraction by a crystal or something. Yeah, by crystal structure. Okay. So now, light behave as a particle property in what we learn now is the photoelectric effect. In the previous chapter, you learned that light behave as a particle in photoelectric effect, and the light do not behave as wave. For photoelectric effect, the light do not behave as wave, because we even deny the light behave as wave in photoelectric effect. Remember, we talked about the classical theory and the quantum theory. We differentiate them. Okay, because in the classical physics, we try to reason that light behave as wave, but in the end, fail to justify the photoelectric effect. Because in classical physics, you think that light behave as a wave, has a continuous energy, and there should be some delays to eject the electron for the metal surface. There should be some delay independent of any threshold frequency. That all doesn't happen. What really happened in reality, mind my word, in reality is the light behave as particle in photoelectric effect. That's the actual happening. It has a threshold frequency. There is no delay in the electron emission. Light seems like the light radiation seems like a particle of energy, or packets of energy being absorbed by the electron to eject the electron from the metal surface. We even discuss about photon. We even discuss about the energy for one particle of light. The energy for one particle of light, which is equal to hf. All these only explains light as a particle. Light do not show wave property in photoelectric effect. Understand? Okay, let's go back to our discussion here. Okay, so from here we can see the light behave only. What I can say like this, I should put a word here. It only light only behave as wave. Light only behave as wave for young double slit and diffraction grating, but light only behave as particle only. Only behave as particle in photoelectric effect. We talk about what E equal to HF, the energy for one particle, or one photon of light. One particle of light. We see the light as a particle. We no longer see the light as a wave. Okay, it only shows particle property in photoelectric effect. Like what you can see here, you see, you see the red light has not enough energy to, it has lower energy than the work function, cannot eject the electron. But the blue light has a very short wavelength, very high energy. It can eject the electron with high kinetic energy. Like you see here, you see can eject the electrons here. So you see the light, the red light is very long wavelength. When very long, we know that we also know about talking about the wavelength. Very high wavelength means very small frequency. Very small frequency means very low energy. Because we talk about HF, when very low frequency means very low energy. Like he say here, no electron ejected because the energy for one particle of light, is less than the work function. That's why not enough energy to overcome the work function, the binding energy. That's why no electron ejected. But when we talk about the blue light has only, I think this is blue or violet, something like that. Okay, let's maybe regard this as blue. Okay, the blue light has very short wavelength. Very short wavelength means very high frequency. Very high frequency means very high energy. Look at this formula, E equal to HF. Very high frequency means very high energy. So if high energy, then it will be more than the work function. And it can eject the electron with high kinetic energy. If you compare, you see the blue and the green one. Green has slightly longer wavelength. That's why it has a lower, this photon has lower energy than the blue light. Blue light really has very high energy. That's why if you look at you compare the velocity of the electron ejected, the photoelectron that accept the blue photon has higher velocity, has higher kinetic energy compared to the green one. This one has higher kinetic energy compared to this one because the photon here has lower energy compared to the photon of the blue one. Okay, it's all because of the wavelength. Understand or not? Okay, so this one we only see the light only behave as particle in this condition. It don't show wave property. So if it shows wave property, then the classical theory also can be accepted. But it don't show the wave property here. Okay, it don't show the wave property here. The light doesn't show wave property here because the classical theory is not accepted. The classical theory is not accepted. Okay, it's being denied. Okay, it don't show wave property here. Okay, but the light only show wave property in the double slit. It show wave property in double slit, but it show particle property in photoelectric effect. So that's what happening. So my question is, light, is it like a wave or is it like a particle? No scientist can explain that. No conclusion can be made. So what we can say here is light is exhibits wave particle duality. Sometimes it's a wave, sometimes it is a particle. There's no conclusion. Okay, but it don't exhibit both properties simultaneously. Okay, sometimes it is a wave, sometimes it is a particle. Okay, let's talk about now. For this chapter, we specifically want to concentrate about electron because previously we talked about light. Light, we always conservatively we think that light is a wave. Turns out it can be a particle. Turns out it can be a particle. Yeah. So normally we think that light is something like a wave. Okay, isn't it? We think that light is a wave. Turns out it can be a particle in the photoelectric effect. Photoelectric effect. But how about electron? Electron, we always think that electron is a particle. We always think that electron is a particle. Particle with a charge negative. We even have the mass of electron. Mass of electron is 9.11 exponent negative 31. We even have the charge. We have the charge of the electron, which is 1.6 exponent negative, just now is kilogram, exponent negative 19 coulomb. We even have the charge. So we always think that electron is a particle because it has a mass, it has a charge. But now, electron can be also a wave. But now, electron in other conditions, it can be a wave. Yeah, so we can, okay, it can be a wave. So we can imagine like the nucleus. You see, where is the electron? Electrons orbit around the nucleus. Yeah, maybe this is the nucleus. Okay, with positive, the proton and the neutron there. Okay, electron, we always think that electron is a particle. Yeah, electron is a particle that orbit around the nucleus. We think that the electron is a particle. We think that electron is a particle that orbit around the nucleus. This is called the nucleus. Yeah, the nucleus. Yeah, but now electron can be a wave. So we don't exactly know where is the position of this electron. Actually, we don't know. We cannot specifically know where is the electron. If we think that the electron is a particle, that means we can know the position of electron at any time. Maybe electron is at this coordinate. Maybe electron is over here. Maybe electron is over here. But we can never know where is actually the electron. Yeah, instead, now we think that electron is not a particle. It's actually like a wave. Yeah, it can actually, like a wave, you know that? Like a wave. Orbiting around the nucleus. Yeah, we can never know where is the electron at any time. We don't know. Yeah, maybe at t, you say at t equal to maybe at time equal to 3 seconds, the electron is over here. The electron is over here. No, we cannot know for sure where is the electron at any time. But we think that the electron as a cloud. We have something we call electron cloud. Yeah, electron cloud. So it's like a cloud, electron is like a cloud, clouding around the nucleus. We can never know where is the position of electron. Where is the position exactly? Where is the position exactly of the electron at any time? We don't know. Yeah, it's all down to probability. It's down to probability. Maybe electron has high possibility is over here, or maybe high possibility over there. But we don't know exact position because electron behave as wave also. Okay, so we talk about electron cloud. So now, that's what happened about quantum. So you see, for electron, traditionally we think that electron is a particle. It's a particle because it has mass, isn't it? It has mass. But for Davison-Germer scientists, he discovered about electron diffraction. The same diffraction like the light. The same diffraction like the light. So electron can also undergo diffraction. Okay, we call it electron diffraction by Davison-Germer experiment. What you see here is, you see, undergo the slit also. Yeah, later we will talk about electron diffraction. What you see, electron also form fringes. Instead of just one fringe or two fringe, it actually form multiple rings. Like you can see, this is actually not light ray. This is not light. This is actually electron beam striking the fluorescent surface. Fluorescence. Yeah, this is actually a fluorescent screen. Why we can see light? Why we can see light on the fluorescent screen? It's not the green light showing. It's not the green light forming this pattern. It's not the green light. This is not about green light. This is about electron ray. Yeah, electron rays striking the fluorescent screen, forming the green light. So what you see here is even electron also form multiple rings. These multiple rings, or we can say multiple bright fringes, or diffraction pattern, is only a property of wave. It's only a property of wave. We cannot explain electron in terms of particle here. Yeah, electron don't show particle property over here. It only show wave property here. So you can see this is the one. Yeah. So what I can say is about wave particle duality is something you can research on. In certain conditions, it behaves as wave. Certain conditions, it behaves as particle. But it don't show both properties together at any one time. Okay? Okay, see you in the next video.